Okay, so here we go. Proposition 5.3.1, again, straight from your book. It says for all integers n greater than or equal to 0, we would like to prove that 2 to the n minus 1 is divisible by 3. So proof again by induction. And I'm going to say let n be greater than or equal to 0. Let n be an integer first, and let it be greater than or equal to 0. So the base case is going to be the case where n is equal to 0 itself. So base case, when n is equal to 0, is it true that 0 is divisible by 3? Well, let's find out. 0 is 3 times something, right? 3 times what? Well, 3 times 0. So the theorem is actually true. So it holds. So that means we should continue on to the next step, which is the inductive hypothesis. So in the inductive hypothesis, we're going to say, suppose that 3 divides 2 to the power of 2 k minus 1 for some random integer called k. So k is now an integer, and we want to show, let's use a different color for this, we want to show that the next integer, so k plus 1 basically, will be divisible by 3. So we want to show that 3 divides 2 to the power of 2, and then the next integer, k plus 1 minus 1. So this is the same thing as saying, this is equivalent to saying that we would like to know that 3 divides 2 to the power of 2 to the power of 2k plus 2 minus 1. So pause the video right now and see if you can test it out. Can you actually prove this? So hopefully you came back from your trial on your own and you're ready to prove. The trick with these ones is that you're not proving any equality, so there's no left-hand side rule and there's no right-hand side. What you want to do is basically grab the expression here and sort of turn it into the old one somehow, or maybe go from the old one to this new one somehow. It just really depends on your preference. You gotta try either way and see what happens. So what I'm gonna do is now I'm gonna say my way of proving it this time is gonna be like this. I'm gonna say consider or take a look at or whatever. Consider the expression 2 to the power of 2k plus 2 minus 1. And this is literally the same thing as 2 to the power of 2k times 2 squared. Okay, why? Because of the same exponent rule that we used a few minutes ago when we said a to the m times a to the n is a to the m plus n. So I'm kind of just going backwards on this one this time. And there's the extra minus 1. Now, why am I doing this? I'm doing this because 2 squared is really in reality just simply 4. So I could go ahead and rewrite this problem as 4 minus 1. But this is not super convenient because I want to show that the thing is divisible by 3. So thinking a little bit more about it, I can now consider breaking the 4 apart into a 3 and a 1. And you'll see why I'm doing that in a minute. If I did that right now, I would end up with basically 2 to the power of 2k times 3, and then 2 to the power of 2k times 1, which is 2 to the power of 2k minus 1. Now, we can already see that this first piece is going to be divisible by 3 because of the 3 that's showing up in it. So that's great. And the second half of the problem has 2 to the power of 2k minus 1, which actually in our inductive hypothesis, we assume that 3 divides it. So, well, if 3 divides it, then what can we say? Well, but we know that 3 divides 2 to the power of 2k minus 1. So there must exist some kind of an integer, I don't know, let's say m, such that 2 to the power of 2k minus 1 is equal to 3m. This is true by definition of divisibility. Well, now that we know that 2 to the power of 2k minus 1 is equal to 3m, we can go back and say, well, the 2 to the power of 2k plus 2 minus 1, which is equal to the 2 to the power of 2k times 3 plus the 2 to the power of 2k minus 1. Well, now that could be replaced with 3m. Okay, so the 3m is basically going to replace the 2 to the power of 2k, and that's because of the divisibility. But this is the same thing as saying 3 times 2 to the power of 2k plus the little m. And since 2 to the power of 2k is an integer and m itself is an integer, this whole thing is going to be an integer. And having 3 times an integer equal to the quantity that we have, that implies that 3 is going to divide the quantity. So 3 divides 2 to the power of 2k plus 2 minus 1, which is what we wanted in the first place. So that's the end of the proof, QED. So hopefully you were able to follow that. If you didn't, let me know and I'll try to explain some more.